So hello all, I am Loredana Cârsta, and I'll be talking today about WasmEdge enabling a universe of compute, which means any language, any source code, any bytecode. In this case, applied to a governable, modular by WebAssembly individual modules, upgradable living system in the form of a blockchain built by and for volunteers. So we'll talk a bit about this multi-execution environment / language collaboration. First, why do this? Second, I will show you an actual live demo on our current testnet. And if I have time, I'll talk a bit about WasM meta contracts, which are WebAssembly modules implementing core features of the blockchain. And about encoding, decoding data passed between smart contracts and execution engines, WasM execution standards, and some examples of WasmX host imports. WasmX is the name of our module, and Mythos is the name of our blockchain. So on why Mythos as a project, I can say that it started 2 years ago from one smart contract, which was the Laurel project smart contract on Ethereum. And this was a very flexible system of peer-to-peer rating of effort, of volunteer effort. And this was done by a continuous voting on a system with reputation. And it was very flexible because it had coefficients everywhere. So this means that we can repurpose the project in multiple ways. One of the ways was even as a governance system for artificial intelligence. And this non-profit project has expanded now in a fully fledged blockchain because we couldn't implement it in other ways. So this is the first project, as of my knowledge, to actually implement a functional multi-execution environment collaborative system. There are other projects that may have maybe 2 execution environments, and it's usually either they are hard-coded in and you cannot add easily other environments, or they have a separate state for them. So I'm talking about a system that already supports JavaScript, Python, Golang smart contracts, AssemblyScript, Solidity with the Ethereum VM, and Rust with CosmWasm. And now to the why. Decentralized public systems are an actual implementation of democracy at various levels of magnitude, of course. And the holy grail of building a decentralized public system is that you can use the system to govern its own existence. So we are talking about one universe in which all of these execution environments share the same global scope / storage. And the way you can actually implement this is if your most important feature is flexibility. So this leads us again to multi-execution environments. And now the demo. I actually have this demo in a more detailed video on my YouTube channel where I have technical videos in case you want to maybe pay a bit more attention. So now this is our dApp in which we deploy and interact with smart contracts. And I have already uploaded a Python smart contract, and the source code is here. Let's look fast about with what it does. So it has an instantiate function. This is when done one single time at deployment, and it just stores a variable. In the case of the Python contract, it stores Python. The JavaScript contract has the same logic, but it stores the word JavaScript. The Golang contract has the same logic, and it stores TinyGo because it's compiled with TinyGo. The Python and JavaScript contracts are actually interpreted by interpreters compiled to WasM, but the Golang contract is compiled with TinyGo into a standalone WebAssembly module. So each contract has its own identifier string here. And then we have two functions, forward and forward get. Forward is a state changing function, it's a transaction, and forward get is a query. And what these functions do, forward takes an initial value, it's a string that you give, and then it concatenates that string with the word Python that it has stored in the contract storage. And then it does a log, a blockchain log or event. And then it receives also an array of addresses. And what it does, it forwards the call to the next address in line, and so on. And it uses the call method from the WasmX SDK that is provided here. The forward get function is similar, receives an array of addresses, and just forwards the query to the next contract. And then it takes the result and it concatenates it with the string that the contract has stored during initialization. So it just adds Python and then the rest. And we'll see this soon in action. So I've already deployed these contracts on chain. I also have the JavaScript contract here, and the TinyGo contract was uploaded as a WebAssembly module. So I got these addresses from the other contract. You have them here, the JavaScript contract address and the TinyGo contract address. And I have here an initial value, which says atomic transaction. We will be communicating with our current testnet, and we have an explorer for this through the Kepler wallet. So we will just do a transaction. Sometimes Kepler delays this a bit, so we'll see soon a prompt to approve the transaction. I don't know if you see it. I'm approving it, and we should see already that the transaction was mined. And in this block, we can look at the transaction here. Let's see. Maybe the Explorer has a bit of a bug, so let's search for the transaction hash directly. Okay, so you can see, and I'll put a link to this transaction here. This is an execution transaction, and you'll see a bunch of logs here that we will look in detail in the dApp because it shows them a little bit better. So what happens is that each contract emits an event. So we should see in the last 3 events, which are of type WasmLog, log. And you get the contract address of the contract that was executed. You also get, this is the encoded data that I just logged, and we can use an ASCII data decoder and we see atomic transaction. Python, this was added by the Python contract. And another interesting information that the logs have are the dependency. So this is the main system dependency, and it tells us exactly what version of the execution environment was used to actually execute this subcall. And in this case, it's the Python interpreter with the version and UTF-8. It's because I've actually used source code to deploy the contract. You can also have bytecode, direct bytecode that can be understood by that interpreter. And now the second log, and let's see the data first of the second log. This was executed by the JavaScript contract, so it added the JavaScript word here. And let's see the dependency. And of course, this is the address of the JavaScript contract. The dependency is on the JavaScript interpreter of this version. And the last one will copy the data, and look, the dependency now is not on an interpreter, but it's actually on the WASI snapshot preview 1 standard because it's a module compiled with TinyGo. Just a moment. Okay. So the last piece of data that we convert is Python, JavaScript, TinyGo. And we can also call the forward get function that receives an array of addresses and is a query. And mind you that the JavaScript and Python interpreters are not AOT compiled right now. So they are not the most efficient as they can be. So we get the decoded data here. It went through the Python contract, JavaScript, and TinyGo. We can remove one of these addresses and do the query again, and we should get Python and TinyGo. So this is a demonstration that you can have 3 contracts written in 3 different languages. Now we got the response, Python and TinyGo. 3 different languages executed in 3 different execution environments that can collaborate with one another. In this case, they collaborated through JSON, the JSON format. So a couple of words about why we chose WasmEdge. It's that we've seen that it moves very fast. We've seen a focus on machine learning and AI, which is something that we're also interested in. Shared memory support and AOT compilation, which gives us efficiency. So we have the flexibility, and with by compiling the meta contracts in the highly used modules, we can also have efficiency. And in practice, we've seen 10 to 30 times lower execution time, especially what interested us was an electronic ID signature verification. We went from 35 seconds to less than 3 seconds. And it can do even better because we actually need to use 2 WASM modules for this transaction, and only one of them was AOT compiled. We had some issues when we compiled both. So if that works, the execution time will go even lower. And we're interested in AOT for at least Linux and Mac OS. Both platforms, we've had some issues with the ARM. Specifically, I tested on an M1 Mac OS, and I had some issues. So we'll see there in the future, but the signs are very good. And we hope to see soon that languages like Mojo, the new Python AI language, will support WASM and will be, we can use it with WasmEdge too. Very short explanation about WASM meta contracts. These can be interpreters, compilers, transpilers, governance and voting contracts, different types of encoding, different types of consensus even, and all sorts of contracts for currencies, points, ratings, medals, and so on. And the idea is that anyone can deploy such a contract. They can battle test it on chain, and then they can decide whether to promote it or not to core level. So you can propose, test, vote, apply on chain, and this on a live running system. You can think of this as hot upgrades. So you should be able to add at any point in time new languages, new encodings, and so on. And for encodings, you can go the route of using a common encoding like JSON for these 3 contracts, or different encodings, because we also have EVM, for example, and you can choose to either embed the encoding source code in each contract, like CosmWasm does with JSON. You can support the encoding in the base layer, or the ideal route for us is as a standalone WASM module. So you can have WASM modules that go from whatever encoding you want to use to the execution environment native memory representation. So this means you have a very fast contract calls between contracts that use the same internal representation. And you also are very storage efficient. And WasmX supports multiple execution standards. This means the multiple entry points that you can have in WasM modules, different memory allocations, reading and writing, and all of these are abstracted out as system dependencies. So when you upload a smart contract, a WebAssembly module, you have these system dependencies analyzed from the WasM smart contract, or in the case of interpreted smart contracts, you can declare them. And also, system dependencies can be, besides these labels and roles, they can be the identifiers for the WasM modules, the so-called addresses. So this gives a lot of flexibility to the system. WasmX host functions are based on raw byte arrays, and these are just a couple of examples of WasmX in C, Rust, and Golang. And that's it. From my side, we are still building. We are focusing on flexibility. And if anyone wants to help and validate this system and test Mythos, they can join our Discord.